So we are doing Mesi over here, and the key thing to do with Mesi is consider the write policy. We have 4 different write policies. Write back, allocate, write back, do not allocate, write through allocate, and write through do not allocate. Great news, whether it's write back or write through, when you have do not allocate, these two function exactly the same. So you only really need to know it 3 different ways because of that. As long as you know that these two work the same way, just learn that, and then learn the 2 allocations, which are a little bit trickier, and there you go. So I'm gonna honestly assume that he will probably put an allocate question, just because he said don't worry about the data part of things, and do not allocate kind of deals with memory a little bit more, because do not allocate says don't allocate in your cache, go straight to your memory. So I would recommend focusing more on these guys. But we're going to do it all 3 ways, since these guys are the same. So let's start out with the do not allocate, since that's a little bit easier. So we're going to do not allocate, and it doesn't matter whether it's write back or write through. It's going to be the same exact thing. So we know memory location Y starts out at 10. So even before we start out, this is going to be 10. So I can write that over here. Now, all the caches are empty. Given the Mesi state of the cache, the value in the cache, and the value in the main memory, assume that the caches are write back, do not allocate. Okay. So first things first, over here, we have a read, we have a write, a read, a read, a write. I think we read to a register, think R, and we write to memory. You could think of a W as an upside down M for memory. So in this case, we're reading. Now reading is always going to be loaded into our cache, no matter what. So it doesn't matter what our write back policy is, because our write policy is only dealing with writes. So with that being said, we are loading the value of Y into our P1. So this is P1, this is P2, P3, P4. What is the value? It's 10. So we are going to be loading memory address 10 into there. It's the only cache that has that. It's exclusive. The next one we're going to be writing. Writing to P2, we see there's a miss. There's nothing here in the cache. Now we need to take into account our write policy. Do not allocate on write back. This is saying don't allocate anything in the cache, put it straight to memory. When, of course, a write miss happens, which in this case it did. So I say, okay, I'm leaving the cache blank. I'm not allocating anything. I put the new value, 15, into our memory. But there's one other step. See, when we're doing this, right, if these are our caches, they're going to be taking the memory bus, going to main memory. And when anything goes on this memory bus, data snooping is going to happen. What that's saying is that, oh, P2 is writing, sending a write on the memory bus. Oh, wow, look at this. Everyone snoops that data. So there's snooping happening everywhere here. They see that there's a write happening. And all these caches are seeing, hey, there's going to be a new updated value to memory address 10. Oh no, this is going to be bad. If I have memory address 10, I'm going to be outdated. I'm going to have a stale cache. So C3, C4 don't care. There's nothing in their cache. C1 has a problem. Oh no, I have 10. And you're writing a new value to main memory? How dare you not tell us? So because of that, when it snoops, an invalid bit gets sent back on the bus to cache 1. So we now know that 10 is not the most updated value. This is invalid. 10 is still going to stay in the cache, by the way. The invalid bit is going to treat the cache as it's empty, and you can easily overwrite it for any new values. But that 10 will remain in the cache until that cache gets overridden. So if there was like a later instruction that said, oh, load a new value into cache 1, then it would change back. But because this is not the case, we are going to be good with that. So that would be the end of that instruction there. Instruction 3, we have another read. We're reading y into R2. Okay. Well, we know that there's no values of y in the caches anymore that I can use. This is invalid. I can't touch that. It's treated as it's empty. We didn't allocate anything to the cache. There's nothing in these guys. I have to take it from the memory. So this is going to be taking it from the memory, right? The memory stays the same. We're not changing memory. And we are going to be loading it into processor 3 now. 15 gets loaded in from main memory. And because of that, it might take a little bit longer than if we just took it from the cache, but we have no other choice. This is now, cache 3 is the only cache that has it. It is exclusive. We keep I10 the same, no changes to cache 1. Awesome. Next instruction, we load y into processor 4 now. Oh, look at this. It's in the cache. I can save some time and take it from the cache instead of the main memory. It's as if you can just ask your neighbor, like, hey, can you lend me a charger real quick, instead of like buying one from Amazon, which would take a lot longer. So this value is able to be shared. So C4 saw that C3 had the value. It asked, hey, can I have the value? And C3 gave it to them. Oh, shoot, I wrote it in the wrong spot. Yeah. So this exclusive is going to become a shared. And we're going to put another shared here. So now they are sharing the same value. This is going to be very important because if there's ever a newer value that gets written in, both of these guys are going to be invalidated at the same time. Think of it this way, like you and your friend have the same answer and you kind of coordinate it, you're doing your homework together, and then someone comes in and says, haha, your answer is wrong. Both of you guys are going to say, oh no, my answer is wrong, and both of you guys get an invalid bit. Okay, main memory doesn't change. C1, same thing, no changes to that. Last step, we have a write. We are writing 20 into Y, into memory address Y on processor 2. So I'm looking at processor 2, and nothing's been written in here. I have a write miss. And because of that, I have to look at my policy, write back, do not allocate. So that says don't allocate anything into the cache, leave that empty, go straight to memory with your value. Don't forget, now we send another write bit on to the data bus, right? Everyone's snooping. C1 doesn't care. You already invalidated me. No change. C3 and C4 see that they have that value. They have that data address for Y, and they see the write. They're going to have an invalid value. The I comes back, and it's sent to both caches that have that value. So this shared value is going to be changed to an I for invalid bit. The 15 still will stay the same.
I got a quick question. So if the write back, if it happened in like processor 1, where the state is invalid, do we just treat that as empty and we just do nothing there and update the main memory? Like, what do we do there?
Yeah, so we do treat it as if it's empty. So if there was, let's say, a read to process to process one, let's say y, we're loading it into R1 in processor one afterward. We would take it from main memory because both of these caches are invalid, and it overwrites it. This invalid is now going to become exclusive and have the new value, which, let's just say whatever the value was. It was 20 because that's what came from the main memory. And so we just treated this as it was empty. The 10 just gets overridden to 20. The invalid bit becomes exclusive since it now has the same value as main memory, and it is the only cache that does that. That makes sense?
Thank you.
No problem. So anytime we have do not allocate, does not matter, right back, right through. We say ignore the cache, write straight to memory, and if there's a write bit, anything that has that value needs to get an invalid bit. Okay, so we are going to move on now to our allocate ones. So this time, let's do write back allocate. So write back is different in the sense that this says write just to the cache and memory when needed. Memory when needed is saying the only time that we're going to push it to memory is when we're at risk of losing the value. It's fine if it stays in cache for a while, but if we end up losing it, then if something gets overridden, we need that cache and we have to save that value to main memory or else we're not going to be able to access it again. So with that being said, what we're going to do is always update the cache and the memory when needed, when we have a write miss. So likewise, we have the value 10 that we start out with. We have again read, write, read, read, write. Reads have no problem. We're just loading in the value from main memory 10 into cache 1. Only one that has it, exclusive. Trouble starts when we have our second one here. 15 is a new value getting ridden to y. Well, I look at cache 2, we have a miss. There's no value in there, so therefore we can't have anything there. So we're going to have to look at our policy, write back allocate, and we're going to first allocate a spot, since right now it's empty. C1 says, oh, look at that, I can help you there. I currently have y's value. C1 doesn't realize that that value is invalid, is about to be invalidated, but it will help C2. That way it doesn't have to go into memory to allocate the spot. I like to think of it as it makes a little box for it. So it makes a little box in C2, and because of that, exclusive is going to be sharing now with C2. It helped it out. They're sharing. Now, C2 is going to say, okay, well, now I'm going to write. So, well, too bad for you. I need to change this value. It's going to write in the value 15. That's the new value. Because of this, it's going to be modified now. It's going to have the new value 15. Remember, when we write back allocate, we don't update the memory yet. Only when something else is going to replace it. This modify is like a little bookmark that tells you, hey, something's changed here. My cache has the updated value. Don't go looking in main memory for that value. Main memory is still going to be 10. Cache is not equal to main memory at this point. Well, we did a write to the cache, and because of that, we need to invalidate this bit. Now, cache 2 is the only one that has that updated value. So now we move on to the next part, right? Where we have a read. And we're going to be reading the value of y into our processor 3. Processor 3 is indeed empty, so we have a read miss. We have to take it from somewhere. We look at our caches. First one's invalidated. Don't want to look at that. Cache 2. Oh, look at this. It has the modified version. Cache 2 has the most up-to-date version. You're naturally going to want to take it from the cache first instead of the main memory because it would take much less time. But now you have to take it from cache because cache has the more up-to-date value. So we're going to, once again, share this value. Cache 2 is going to share its value to cache 3. But before it loses this modify bit, because the modify bit is the only thing telling us that this has the updated value, not main memory, I gotta flush it to main memory. If I want this value to change to an S to show that I'm sharing it, I have to first give it up to main memory first. So what I'm going to do is I'm going to flush it first. We're going to flush the value, so move it into main memory. At this point, it can be called exclusive. Exclusive means cache is equal to main memory. Exclusive being only one thing has it, shared being more than one thing has it. But both have the same meaning in that cache and main memory are both up to date. Now that I'm in exclusive, I can share it. I make the little box. They both have share, and I share over the value. It's a read, so I don't have to worry about any backstabbing on cache 3's part. Now, it went from modified to exclusive in the process of flushing it to main memory. That way I can share it easily. And we have the state as shared now, and they both have the same value. C1 stays the same, and that's all for that part. Then we go into instruction 4. We're going to just do another read, this time to processor 4. Well, this is nice and easy. We're already sharing. I can just share the value again. So now we're going to share the value between 3 processors. Cache 1 stays the same, no changes in main memory, and we're all good with the read. The reads usually don't cause problems. It's the writes that do. And now we have another write. This time we're writing 20 into our address Y on processor 2. Right now, processor 2 has a shared status and 15. This has shared 15, shared 15. Current data address is 15, I, and 10. Now, we're going to be doing another write. I look at C2 and I say, there's a write miss. It's not the same value. I need to overwrite that value. So what am I going to do? I'm going to first allocate a spot. Well, there's already a spot right here, since the address Y is already there. And all I'm going to do is just change it to the new value, 20. Upon doing that, I know now I don't share it anymore because now it's not the same. I'm going to make a modified bit here. Because it's write back allocate, I'm only writing to the cache. This 15 in the main memory is staying the same. But there was a write bit that went through the data bus, and because of data snooping, cache 3 and cache 4 see they have an invalid value. And because of that, we're going to be left with invalids on C3 and C4, modified for C2. C1 just stays the same because we didn't do anything with it. And the program is going to end at this point. So if you notice that this modified bit is going to stay, and it's going to say, okay, C2 and the main memory are not the same. If we need to take something, we need to take it from C2. So if there was a future instruction, like what we did before, we would take it from wherever we have the modified bit, not main memory. So this is write back allocate. Questions?
Isn't it 20 at the end or
Main memory?
still 50? Yeah.
So because it's write back allocate, even though the program ends, we're actually going to be leaving it the way it is because there was no other instructions that overwrote this value, so there was no need to flush it to main memory. The only reason we would flush it to main memory, meaning that main memory and the cache would have the same value, is if something else needed to use the cache.
Oh, okay. Because it was just a bit different from the answer key. I was just wondering.
Yeah, no problem. Actually, yeah, on one of these answer keys, it actually had the same problem. I checked with him on that. So, yeah, don't worry. It is supposed to be left as 15. If this was right through, which we're going to do next, then the value in the main memory is always going to be the same as the cache. Then it would be the same. So it was a good catch. So on that note, let's do right through now.
Wait, so for that one, for the the first rate, as long as it's basically not being needed or shared, then we keep it as is and it doesn't get sent to main memory.
Yeah, you got it. As long as the cache itself is not. So it's not always the value. If there was like a read done on processor 2, actually, and it was going to be doing a read, let's say R2, and it's going to do the value of Y or something. Or some other, let's just say X for a different value. Then we see that the cache is in use, but we need to use that cache because it needs to be written to processor 2, and we only have one slot for each. There's only one cache. I need to use this value. Sorry about that, but you gotta go. Value 20 of Y. This is another instance of when we have to flush it. Anytime that cache needs to be used by something else, this is a case of when we have to flush it. From modified, we go to exclusive because the value 20 that was here will now be flushed to main memory. And now cache and main memory are equal. So that's what exclusive is saying. Cache is equal to main memory. Now I'm free to put in whatever value I want. And in this case, it would be whatever value X gives me. And it actually stays exclusive. You can think, okay, it was exclusive because it had the value of 20. I overwrote it to be the value of X, and it's still the only cache that has that value, so it still stays as exclusive. So that would be kind of an example of overwriting the cache in that way.
Got it. Okay, thanks.
Yeah, no problem.
One more. Just to be clear, does it matter how you put the C state, as in like instead of S pointing to M, you can just put M. Does it matter? Or
like over here?
yeah, like S pointing to M, or you can just put M on it. Does it matter?
All he cares about is the last state, so your answer is just
Oh,
really going to
okay.
be M. But let's say you had to, it was something that went through multiple states, like over here, it went from M to E to S. It doesn't hurt to kind of show that you're going from one state to the other.
Okay, thank you.
No problem. So the last one that we're going to go over is write through allocate. And in this case, we start out with 10, same as before. C1, we're going to be writing the value of y to R1. So this is going to be a read miss because there's nothing in the cache right now. I put 10 in there. I took it from main memory. They're equal. And this is the only cache that has that value. It is exclusive. Our next one is a write. We are writing the value 15 into processor 2's cache. There's nothing here. We have a write miss. What's our policy? Write through allocate. First things first, I need to allocate. Think A for allocate, A comes first. So C1 says, let me help you with that. I'll make you a little box here. Right? This started out as E10. I'm going to allocate you a little box. Because of that, we are both sharing that box. Now, C2 says, okay, great. Sorry about that, but I am going to end up backstabbing you now because I'm changing my value. You write in your 15. The value is modified. But since this is right through, we can't end on a modified state because our main memory and our cache must always be equal. I will now transfer this value into our main memory. They're equal? Great. Now I go to an exclusive state since they're equal. This shared state has the invalid bit. As soon as I wrote to memory, that's a sign. Oh no, C1, sorry, your value is currently invalidated. C1 is very upset because they just got backstabbed. What do you mean? I just helped out C2, and now you're saying that that my value is invalid? Yeah, it's as if you helped someone out with their coding project and they took your name off of it and revoked all your editing rights. That's kind of like what's happening here. So we go from shared to invalid. 10 still stays there, and we end up with having cache 2 having the exclusive value of 15 equal to our main memory. Going back to read, we're now going to be reading that value to processor 3. Processor 3 can take that value right from cache 2. It has an exclusive value, so it is up to date. They're going to share the value. Allocate a little box, share your value. No writing's happening, no other changes are necessary. Main memory stays the same. Same exact thing for processor 4. Now we're going to have 3 things that are sharing. C4 can take that from either cache 2 or cache 3. Doesn't matter. They all have the same value. Main memory doesn't change. C1 does not change either, since there was nothing that changed it. Now we get another write. This is going to say processor 2 is going to be writing 20 to address Y now. So let's see, what do we have here? Shared 15, shared 15, shared 15. Okay. Well, now a spot's already been allocated, right? And it's taken up by this 15. At this point, we're going to modify the value to the new value, 20. But since it's right through, we also need to pass that to main memory. At this point, when the write happens, everything snoops and sees, oh no, it's invalid. So anything that had that shared bit, it's a nice easy way to kind of backtrack and see, okay, these two other caches had that value, so these two caches also need to get invalidated. Now that cache 2 and the main memory are equal, and it is the only value that has that correct value, it will now be exclusive. So we now go from the shared to the modified to ultimately exclusive. And we have the updated value in main memory. C1 stays the same, and we've invalidated C3 and C4. So this is a case in which main memory and our updated cache were indeed the same in the end. So with that being said, this one, they have the same value, so if they ever need to get that value again, they can take it from the cache or the main memory. Both are the same. In the other example with write back, they were not the same, and you would have to have taken it from cache 2. So that's the difference between the write policies. Questions? Do you want to do another one of these? Because there is a second problem, or there's also a harder, messy one. What do you guys want to do?
Can you go over problem set 7?
Totally.
Thank you.
No problem. So problem set 7, yeah, I had fun with this one because I realized midway through that his answer was mixed up. And for some reason do not allocate had a modified state in it, and I questioned every single thing that I was learning.
Yeah.
But yeah, now I'm good now. So let's definitely do this one. Let me just paste in all the parts to it. This is on like 3 different pages. Okay, so we're gonna start out with write back on this one, since this is the one that actually did have the answer to it. We had write back. Okay, so we're doing write back, allocate. So one thing is, he said don't worry about the data aspect of things. So we're literally going to ignore all these data columns. Half of the answers are kind of wrong for the data columns too, so really just don't even worry about that. He said that's not going to be on the test, so there's no need to worry about the data. All we care about mostly is the states and the addresses. So this one's a little bit trickier. We can still do this. So this is our initial cache states over here. And this is cache 1. This is cache 2. So this time we have a couple of different caches. It's used by direct mapping over here. So if you remember direct mapping, you take your address and you mod it by whatever number it is. In this case, we mod it by 4. So address 4, if 4 is modded by 4, you get 0. That's why it's an index 0. 1 is an address 1, 2 and 2, 3 and 3. In this case, 8 mod 4 goes in evenly, therefore it's an index 0. 5 mod 4, there's a remainder of 1, you get the picture. So with that being said, these are the initial cache states, and we're going to be going through these rules right here. I don't know why they don't have the arrow on them, but the arrow is always going to be going to the left. So that's also the way that it was in the answer key too. So that's the way we're going to be looking at that. So what we're doing here is we're writing to a memory address, right? So in processor 1, so P1's cache, we're going to be writing in to address 4. So address 4 is already here, and it's currently exclusive. We don't care about what the data is. Since it's exclusive, right, we know that this is currently the up-to-date value. So it is the same as whatever is in our main memory at this point. So that's great. That means that this is actually going to be a hit. We have the same value here that we have over here. But this time, since it is a write, we'd have to write in the value that's there. So the address itself is a hit, but the data is going to be different. And while I said don't worry about the data, we know that it would be different because we're loading in R1 here. So anytime that we're loading in a value and we had a write miss, we look at our policy, write back, allocate. So we're going to change this to be a modified version now. So this now is going to be modified. So it will not be the same as what is in main memory at this point. There is no other cache that has that same address to it, right? So because of that, we stay at modified. If there was another address 4 in P2's cache, then we'd have to see about invalidating that. But since P2 and no other value has that address, it doesn't matter. Yes, there was writing that happened. Yes, there was data snooping that happened, but there was no issue with that because no one else has the value. Great. So now this is modified. We still have the same address here, but there would be a different value inside the data. So again, he said, don't worry about the data. So now we go to our next part here, P2. This time we are going to read to the register. So we're reading in address 7 into our processor 2. So if we were to do 7 mod 4, we get a remainder of 3, right? So we know we're going to be over here, in index 3 in processor 2. Now I see that there's a different address here. There's a 3, but we're trying to load in a 7. So this 7 is going to kick out the 3. So we're going to now change the 3 to a 7. This is now the only cache that has that value, right? Because there was a 3 over here. This was invalidated though, so there was no issue behind that. And then this 3 would now become a 7. Something to keep in mind, this was initially modified though. So technically, we would change that to exclusive, and this value, whatever was the 3, would get flushed to main memory at this point. There's no place for main memory here, so we only care about the cache, I guess, but at this point we'd have a main memory flush. And the value, the address of 3 would be flushed to main memory, making that exclusive. We overwrite the value into 7, and we can think of it being exclusive yet again. You only really need to have the 1E. It just sometimes makes it a little easier to think, okay, this was exclusive because we flushed the 3. This is exclusive because now we have 7, and this is the only one that has the 7. The professor only cares about the end state, so however makes it easier for you. Okay, so we have M, we have a 7 here, And we have E here to go to the next part. So now we're looking at processor 1. And this time we're going to be writing R3 to address 2. So this is going to go in this spot right here. What is 2 right now? Shared. And it is the actual address 2. Something about this that didn't make much sense is that on the opposite side, the address was 6 and exclusive. So I'm not sure where this is sharing, honestly. Maybe there was like a third processor somewhere that actually had the value, but technically if you were to overwrite one of the values, it would no longer be shared. So I'm not really sure where that exactly moved from, but yeah. At this point, though, it really doesn't exactly matter too much because we're going to be writing over to R3. So, writing into address 2, whatever the value of R3 is. So, because of that, whatever's in here, whatever value is in there, data value, which we don't care about, it's going to be modified in the end. Yes, the same address is going to be there, but we're modifying a new value in there. So since this is shared for some strange reason, it's going to be changed to modified. Remember, shared and exclusive mean that the value is up to date in main memory, so we don't have to worry about any flushing that happens. It just stays as modified, and at that point we would have the same address too, but with a modified data value. So now going on to the next part here. Modified here, modified here. This was a 7, exclusive, exclusive. Oh, oops. I keep writing in the wrong spot. So now what we're going to do is... Sorry, what was that?
Hello? I have a quick question. If we go back to the third one, let's say cache 2 had an address called 2 and state was also shared. And in cache 1, you changed it from shared to modified. So would you change in cache 2 be invalid?
So, yes. So because they're sharing the same address and you're overwriting that address, so let's just say 2 was equal to 3. Address 2 was equal to 3. Both of these are shared, so they're both sharing that same address that has that same value. Now let's say you make 2 equal to 4 over here. They're no longer the same. So with that being said, we would change the shared and make it invalid because this cache in processor 2 has the old value, 3. That's currently a stale cache. So yeah, something tells me I think there was supposed to be a 2 here or something. Yeah, this is honestly a really, really weird question, to be quite honest. But yeah, if that was indeed a 2, you would invalidate that. Because anytime a write happens, you check to make sure that it was not on the data bus. Because you always do data snooping. So at this point now we're going to be doing another read. We are reading address 1 into processor 2. Currently in processor 2, index 1, because we know if we were to do 1 mod 4, we would get 1 at the end. We have the address 5. We're going to have to overwrite this, but before we do, 5 is shared for some strange reason. Yeah, I really don't know why that is shared, but because of that, that means the value is up to date in main memory and also in the cache as well. So with that being said, we're actually all good. And we can easily just overwrite this value at that point. So what we're going to do is we're going to now load in 1 into this place. So we're going to change our address to 1. No flushing needed because it's just shared. Now, this is actually going to have the same address here. Now, let's make sure 1 is modified, right, over here. So we could actually just take it from this address here instead of going into main memory. So we're not just gonna change this from shared to exclusive. We're gonna just share it from here. But we can't be modified and shared at the same time. This is where flushing is gonna happen now. We have to first get rid of the modified, flush this to main memory. So main memory is going to have that address 1 in it. This is now going to be exclusive because main memory is equal to our cache. Now we can easily share it. This is going to share here. So it's going to look as if it went from shared to shared, but it's going to be 2 different things that were shared. The 5, and then we allocate the value from our 1. Since no writing is being done here, all we're doing is just taking the value from processor 1 and sharing it to processor 2. So with that being said, we're going to end up having both caches having the address 1 and both of them being shared. And lastly, we have processor 1. We're going to be writing into memory address 6. So 6 we know is going to go into address 2. Let me just write in everything else that was in there. So we want to now put in 6 over here. First, I check my caches. Oh, look how convenient. 6 is in processor 2 right now. That's really great for us. That makes our life so much easier. It's currently in the exclusive state. So while I am doing a write, I can first allocate the value by sharing it from processor 2. And that's just what I'm going to do. But before I do that, I see there's a modified value here. I got to flush this out before I'm actually able to get a shared value here. So I'm going to do a little flushing. Flush this value out. Main memory is going to have a value of 2 in there. Again, there's no spot to put the main memory, but you could imagine in that spot 2 in main memory, you're going to have address 2 there. Since main memory and cache are equal, we're now in an exclusive state. Now at this point, I'm free to share the value. I can now allocate room for address 6 here. Both of these become shared. They'd have the same data. But now I'm going to be changing the value. I'm going to be now writing over it. Since this is write back allocate, we're going to modify it. So it's not going to be the same as main memory anymore. Anytime a write happens, anything that was sharing that value, boom, becomes invalid. So we're going to end up with this final state being an M for modified, showing that it was written. This one being an I for invalid. And this is the end of that crazy question. That was written extremely poorly. Does that make sense? If you want me to go over any part of it, let me know.
Can you go over how it went from M to S and then back to M again?
Totally. So this started out as an M, right? That was just what was stated here. Oh, wait, hold on. That was... Oh, I'm sorry, over here. This was changed over here because we modified this value back here. This stayed modified until we went back over to use that piece of the cache again. Right? We're going to keep a modified state until we have a need to change the cache. If we need to use the cache again in any form, that's when we need to do a flush. Well, now I'm going to use this cache again. I don't want the address 2 in there anymore. I want to have the address 6. I need the address 6 in there allocated first before I'm able to write over it. So I see, okay, I want to put the address 6 here. I have a modified bit here. I can't afford to lose the old value of 2 because this is the current most updated value of address 2. I got to flush it first. When I flush it, the first thing I do is I push this over to main memory. So now, whatever's in address 2 is in main memory. Anytime main memory is equal to our cache, we're now in an exclusive state. It's exclusive at this point because it was the only one that had that value. That value is now in main memory. Because main memory is equal to cache, we're all good, exclusive. Now that it's exclusive, the value is saved. I can overwrite this value. So now I'm going to change the value from 2 to 6. P2 has the value 6, meaning I can actually share these two values. So P1 and P2 is going to share over address 6, so we can allocate it. All that's saying is, I'm going to give you a little box to put your value, your address 6 in there. Now they're sharing. Both of these change from exclusive to sharing, since they go from having different values and being the only ones that had those different values to sharing the same value, 6. They both have address 6. They both have a little box to put their 6 in. But now, P1 has to do the right. P1 is going to stab P2 in the back. You helped me, but guess what? I'm going to change my answer in the end. I'm going to change it now to whatever the value of R5 is. Because of this, now this shared over here is going to be modified. So the value of 6 is going to be whatever R5 is. This is no longer equal to the value of 6 in P2, which is whatever value it is. Again, we don't care about the data. Because of this, P1 has a modified value. The second we wrote to our cache, there was some data snooping going on. P2 said, hey, what are you up to, P1? You changed that answer? You changed what that address was equal to? How dare you? I was helping you and now you backstabbed me. Now at this point, P2's cache in this spot is invalid. These two are no longer equal. Let's just say hypothetically that this one was equal to R1, just for simplicity's sake. Now, P1's address 6 is R5, P2's address 6 is R1. They're different. This one has the more up-to-date value. This gets the modified. This one gets the invalid bit. See where helping gets you? Make a little bit more sense?
Got you. Yeah.
Cool.
I just forgot about the R5 part that you had to like update. Yeah.
Yeah, he said not to worry about the data, so. But that's essentially what's going on. There is stuff happening behind the scenes with the data actually changing, but we're just dealing with the actual address itself. So we could also do do not allocate as well, or write through allocate. Since we don't have access to the main memory, I'm just going to do the write through allocate one, since do not allocate would kind of just be resulting in a lot of these caches kind of empty. And we don't really have like a main memory column, so that might get a little weird quick. So so this time what we're going to do is we're going to be doing write through allocate. So the difference between now what we're going to have with write back and write through is that it gets written through to memory. So with that being said, there's no need to have a modified value at the end. Values will be modified, by the way, but they're going to go from modified to exclusive extremely quick. So you're going to probably see something like it's a modified value and it's switched to exclusive just like that. Data flushing happens at each point because the main memory and the cache are always going to be the same. So with that being said, again, we don't care about the data. We're going to start out with, over here, we're going to be doing a write to memory in P1. So 4, address 4 is actually currently in here. It's currently in the exclusive state. Since we are doing a write, this is going to have a different value in it. And because of that, we're going to have to change that. We're going to write it. So we're going to change this from exclusive to modified, but this time we're changing it back to exclusive because this last time we only wrote to the cache. We didn't write to main memory. This time we're writing to cache and main memory. Just like that, boom, it's both updated. You can technically just keep this as just E since it stood as E, but it was E for a different reason. It was E for the original address of 4, the only one that had that original address. Then it changed, the modified, to a new address of 4. And again, the only one that has it. The other cache, P2 cache, does not have that value. So that would be it. So
If this was a do not allocate, it will stay as M.
Yeah.
Okay.
So the cache would not change in that case. In that case, we would just go on to
update cache.
Yeah, so if this was do not allocate, we would just kind of flush that value. Yeah, actually, you know what? You wouldn't even have an M. If this was do not allocate, you would not have an M. So, what is do not allocate doing? it's just saying essentially screw your cache, just go to memory by default. If you have a write miss, go to memory. So because of that, anytime that you have a write miss, it gets written to memory. You have no need to modify the cache because the updated value is always going to be in the memory. I remember he actually said that to someone who wanted to do this problem, or like a different problem like that, he said that just get rid of the M in that case. So if we wanted to do this like do not allocate, then we would just have to kind of change that to like an E or something else. That's actually probably why that answer is messed up, because it's the same answer as the write back allocate. Okay, that actually makes a lot more sense. But yeah, in conclusion, if there is an M, then that can only happen when you actually do allocate something. So that was a really good point to bring up.
Oh, okay.
Yeah, so in this case though, like, you know, we switched it to exclusive, because again, it wrote through to from cache to main memory. They're equal. Boom, exclusive. So now we are going to P2. We're reading to the register, address 7. So where does address 7 go? Well, 7 mod 4 is 3. It goes into index 3. It's going to go in this spot here. So what is currently in this address is address 3. And address 3 is currently in a modified state. Before we do anything, we need to flush this value out. Now, technically, this probably would have been flushed already, since you don't really stay in a modified state, honestly, when you're doing write through, as I said before. That's why this whole question is kind of weird, but let's just, for practice, let's flush it out. We're going to flush this out, so in our main memory, we're going to have that address 3 in there, whatever the value is, whatever. Since main memory is now equal to the address in the cache, it's exclusive. Awesome. Now I can easily overwrite this. Now note, there is something to keep in mind. If this was a shared value with the 3 in P1, we would need to keep that in mind. But this is currently invalidated, so there's no problem with that. We're going to just change that. Boom, 7. It is currently still exclusive, right? We can think of it similar as before, where you cross out the E for having the 3 being exclusive to now having the 7 be exclusive. But again, it ends up just being E in the end, so that's totally fine. So now we're going to go to instruction 3. We are writing to this memory address, address 2 in P1. Well, good news, the 2 is right here. And what is the 2? It is currently shared with what? Who knows? This question is really bothering me, but yeah. Either way, shared and exclusive function the same. It's the same as in the memory. Great. Won't be for long. We're going to be changing that for a bit. So we're going to be changing that to the value in R3. This is now going to be modified to whatever that value is. But again, write through. I should probably change that, since we're doing write through allocate. Sorry if that confused anyone. This value gets flushed out to main memory. So our main memory has that value. We are back to being exclusive, since now it's equal and there's nothing else that's sharing. If there was something else that's sharing, great, it would be shared, but there is nothing else shared. This is the only one that has that modified value. So the key with write through is you're passing through modified. You never stay in modified when you're in write through, because why would you? The whole point of modified is to show cache is more up to date than main memory. They're both up to date. No reason for that. Okay, next part. We are in the exclusive state here. Address 2 is exclusive. This is 7. This is exclusive. Cool. Processor 2 and we are going to read to the register. This is going to be address 1. Address 1's not in here. 5 is currently in a shared state, meaning that it's up to date with the main memory. Okay, awesome. So I can just literally overwrite that without a problem. I'd have to keep in mind whatever it's shared to would end up getting an invalid bit, but what is it shared to? There's no other. I really think this question's missing an extra cache or something, because if that were the case, something else like in P3 would have also had a 5 that was shared to this 5, and that would have to get an invalid bit. But there's nothing here that is being shared to, so I can honestly just change that easily to 1. Right, this is just a load, just a read. And I can actually take that from our 1 over here. So in address 1 here, we have a modified value. Modified needs to get flushed out before I can actually share it. So that means we're going to flush this value out. Main memory will get a value of whatever 1 is equal to. And now, yay, it's exclusive. They're the same. Now I can easily share. I share this value. I share this value. This technically stays the same. They're both S's. And with that being said, that part is now done. We have a 1 in here. It's just a read, not a write. All we did was just share the value. Beforehand, we just had to flush that out. That's why we had the M and the E there to show we flushed, then we shared. If you want to think of it as a way of doing it, like flush it out, like, and then you share it with someone else. You have to make sure that you flush out that M, because there's no other way you can put an S in there. You can only have one state at a time. And last part. P1, we are writing to the mem address, and that is going to be address 6. What is address 6? Well, that goes in index 2. Something else is there. And then the 6 has an exclusive. Okay. So there's good news and bad news. The good news is there's an address 6 here I can easily share with. The bad news is something is in here already. But there's more good news. It's exclusive, showing that main memory is equal to this. I can overwrite away. No need to flush. So with this, I can just feel free to share this value, the address 6. This shares over. I allocate my spot. And now they're both sharing that same value. Now this is a write though. So once I allocated that spot, now I'm going to write a value in there. This S is going to be modified. The second I write something, you backstab everybody else. This is now invalid. This is a different value than this. They're both address 6, but R5 is in address 6 now. This address 6 could have had like R1 in it, let's say. P2 allocated the value. It helped cache 1, and then cache 1 backstabbed by changing the value. So now this is modified, but we are indeed in write through. So we don't stay in modified for too long. That value now becomes exclusive again because that value goes off to main memory. Main memory and cache are now equal. Everything is right in the world, and this would be the final answer for that one. So moral of the story, you're only going to stay in modified states if you're in write back. Write through, you're going to go right through the modified state. Haha, see what I did there? Okay, let's go on to the next set. Any questions first with this?
Our problem set was crazy. I hope it's not like that on the test.
Yeah, I'll be honest, I don't think he would do something crazy like that because, like, again, you can't really have that. And like there were a lot of things wrong with that question. I think a lot of these come
A
from
lot
like
of typos, I think.
Sorry, what?
I think he made like a lot of typos too on that one.
Yeah, a lot of the answer keys do have typos in it, which is a little frustrating, but see, it's bad when I've honestly like kind of memorized where the typos are, and I'm like, "Oh, I'm not falling for that trick again." Yeah. So, okay, so that was problem set 7. We did 6, we did 7. What's 7B? There's 2 more messy problems in 7B. Do we want to do that? Want to switch over to raid for a bit and then go back to messy? Maybe one more.
We could finish it
Okay, yeah, maybe one more messy, and then
on 7B, right?
yeah. So we're gonna be on 7B now. I have a feeling I'm gonna be dreaming of messy tonight. It's gonna be like modified states going all through my dreams at this point. Okay.
Yeah. At least it's at 5 o'clock and not in the morning.
Yeah, for sure, for sure. My brain does not work like earlier than 9 a.m.
For this homework, he only gave one solution, right? He didn't give the various solutions, like various ways.
Nope. This is just right through, allocate on right miss.
Okay.
Do we want to try it a different way?
I mean, we can go through the normal way. I mean, it's fine, whatever. I was just wondering if cause I did the different versions and I emailed them to him, but he has not responded yet. If anyone else has emailed him different versions, I'm curious if they have the answers, but I don't think so.
I made him go over, I think, few. We can go over that later on, but yeah, I just
Okay.
made him do a few of the cases, different scenarios.
Different scenarios. Okay, yeah, we can do that at the end then. That's perfect. Thank you.
Yeah.
All right, cool. So yeah, if that's the case, we'll start out with this is right through allocate, and we can kind of just go through that because if put it this way, if we all get like the same answer on the other ones, then like I think we're pretty good. Yeah. So, okay, we're doing right through allocate on right miss. And just to keep in mind, each data memory location has an initial value of 2, and each register is initialized to 1. And I'm just doing the same old, same old. Cool. So let's see. We are starting out with processor 1. Just draw lines going down here. And we are going to do a write to our mem address. And mem address 3, this is direct mapping. It's going to map to cache number 1. What's in cache number 1 right now is an invalid 3. We treat this as if it's just empty, right? I do happen to see that there is a 3 in another cache 1 in processor 3. This makes our life so much easier. If we can take it from another cache, then that's fantastic, right? Remember data snooping. It works both ways, read and write. If you're trying to read something, someone else can help you read it by giving it to you. You could think of it as lending a book from a friend rather than going out to buy it on Amazon. So it's the holidays, I guess. I have Amazon on the brain. So we got 1, we got cache 1, 3, and P3. I can easily share this. So again, this is invalid. I can just honestly leave that alone. That's not a problem. And we're going to have both address 3 here, and we're going to share it with each other. So this goes from exclusive now to shared, right? And now this is, though, a write. So after we do the initial allocation, right, write through allocate, we then are going to modify the value. We're going to do it now, we're going to do a write. So now the state is going to go from S to M to show that it was modified. And the second there's a write, anything else that had that same share, automatically invalid. Backstab. Keep in mind this is write through. If we stay in modified, we don't stay in there very long because memory is going to be equal to the cache. We are back to being exclusive. Memory and cache are equal, all is right in the world. P3 still stays as invalid. Okay, so this was 3, exclusive, 3, invalid. All right, now we're in P2, and we're going to write to address 8. This goes in cache block 0. And look at this. Cache block 0 already has an 8, and it's exclusive. Wow, that's amazing. In this case, right, we have to just update whatever the value is with our 7. So we do have a cache hit. All we need to do is change the value. So again, this is write through. So we can think of it as it goes from exclusive to modified, right? We change the value and then back to exclusive. There's nothing to share. We don't have to invalidate anything. None of the other caches have the same value. So we're going to be left with exclusive on this one. So it's going to look like it's unchanged, but essentially we go from exclusive, modified, back to exclusive. Why do I keep writing in the wrong box? All right, P3, read to the register. We got address 3, and address 3 is going to go into cache block 1. Too bad this is invalid because it would have made our life so much easier. But what we do have is we have it in a adjacent cache. P1 has that. So I can just feel free to share it right over. Okay, you're going to cough that up. Thank you very much. And now both of these guys are sharing that address. There was no change in the value because it was just a read. So they both have the same shared value. Okay, now we have P1. We're going to write to the mem address 4 in P1. This is going to go into cache block 0. What's in there already? Well, we already do have the address 4. It's currently exclusive. But we are going to end up writing a new value there. Before I do, I just want to check. The only other 4 is here. It's already invalid. We treat that as an empty block. There is no problem there. So with that being said, we got 4, we got exclusive. We're going to write, and then we are going to have it modified. Because it is write through, we don't stay in modified long. We go back to exclusive. It looks like it's not changed at this point, but the value itself has changed. But again, we don't care about data. So with this one, it still stays as exclusive. Okay, next one. P3. Just finish writing these in. I find that if I don't write these in each time, I just lose track of where I am. Now we got P3. we're going to do a read to the register, 4 to R2. This is going to go in cache block 0. So this has already a 4 and an invalid in here. But invalid's not going to help us. We treat it as if it's empty. The good news is, look at this. We just put a 4 in there. That's awesome. We can just easily share this over. The address is 4, goes from E to S to share, invalid to S. And with that being said, we have both of those shared. Okay, last two, 4S, 3S, 8E, 4S, 3S. And we got a read to the register, address 4 in processor 1. Okay, so this is actually already in here. It's shared, there's just a read here. So the fact that it's shared is totally fine. It can technically read from either of those, but since we are requesting it from P1, there's no need to do any additional things here. No changes happen. And then the last one here, P2, we have R1 getting written to mem address 4. I'm too lazy to rewrite this. I'm just going to do it in this box here. P2, this is going to be mem address 4 is going to be done here. We have to allocate first. This is the wrong value. We don't care about that 8. That 8 is going to get kicked out. We are doing write through. Therefore, this is exclusive. There's no modified, no need to flush. But we do have to do a little bit of sharing. So what we're going to do is we are going to share from the processors that do have the correct address 4. So I can share easily. Boom, address 4. But now I want to do a write. This share is going to become, you know what, I don't have enough room. It went from exclusive to shared. The shared is going to turn into modified because you're going to modify the value. The second you have a modified value, these guys get invalidated. Cache 1 and cache 2 helped out cache 1 and cache 3 helped out cache 2. But that's no good because now cache 2 decided to backstab them and change their value. It's modified. We are in write through. We don't stay in modified for long. We are back to exclusive. So ultimately that changes to exclusive. That's the end of that one. Questions?
Wait, sorry. Isn't it? I thought it only goes to modified on write.
It only goes to modify
But it
on
was like
write
a
back?
load. It was a load, so doesn't it stay?
Oh, I'm sorry. I wrote it in this
Go
one.
through that one.
I wrote it in this one, but it's for this
Oh.
one. There was no change in
Oh,
this
okay,
one.
okay.
Yeah. So this,
Alright.
what I
I was
wrote
reading the
here,
wrong box,
was
sorry.
literally just for that. Yeah.
I got you.
But yeah, 100%. If it was a load, you would not have changed it like that.
Can you zoom in a little? I just want to screenshot it.
Yeah, go ahead.
It's a bit blurry on my end. Okay, there you go. Yep.
Is that good?
I got it.
Awesome. All right. There's one more messy question. I guess let's just finish it up. So this one again deals with the data, but he said don't worry about the data. So therefore, we are not going to worry about the data. So what are we doing here? Well, we are doing write back and write back allocate. And yeah, cool. So write back allocate, this is the one that will stay in modified for certain times. And we can actually see this because the initial state actually has a modified value in there. So that's kind of like our little hint there, like, there's modified values here. I guess we can stay in modified. Cool. So we're starting out with P2, and we are going to read to the register, read 8 to R1. Now, here's a little trick. He's trying to trick us on this one. 8 does not have address bars. These are not the same. This is address 8, this first one. This is the number 8. This is saying straight up load 8, the number, into R1, not the address, meaning this does not go to memory. If we don't go to memory, we don't do Mesi. Therefore, there is no change here. So that is a trick question. I also spoke to him in class alongside this, and he said, like, I think someone told me, like, oh, does an R-type instruction use Mesi? What's an R-type instruction again? This is the one that does, like, arithmetic. Like, R1 plus R2 gets stored in R3. Does this go to memory? No, it does not. These are registers. Registers are on the CPU. If you don't have address bars like this, you are not going to memory. If you don't go to memory, you don't use Mesi. Because what is Mesi dealing with? Memory allocation. You're dealing with your cache. There's no need to use the cache if you're just using numbers. You can just take 8 from your computer. Like, it's not being stored anywhere. It's just a number that's being crunched. So, no change. And if they gave an instruction like this, also no change. Beware of that, because I have a bad feeling he's going to put that on the test. Yeah. So now we are back to address bars over here. So this one indeed will use our Mesi for P1. So we are doing a write to our mem address, R1 to address 8. All right, we are doing direct mapping. So where does that go? Well, we know 8 mod 4 is 0, so it goes into cache block 0. It's going to be right here. What's in there right now? 4i. Okay, invalid. Treat it as if it's blank. I'm just going to first do a little bit of allocation. Let's see, can I allocate it from P2? Yay, look at that, it's right there. Get to save a little bit of time. But beware, we have an M. Gotta flush it before we share it. So M now is going to be flushed to main memory. So now we can think of main memory has now a value of 8 in its block 0. And this is now exclusive because cache is equal to main memory. Hooray. Now I can just put this into my P1 easily. It's exclusive. I can just share that over. Let me go and allocate that. I put that in. They're sharing. Unfortunately, this is not a read. This is a write. Now the backstabbing happens. P1 is going to change the value to whatever R1 is. I go from shared to modified, and we are doing write back, right? Yeah. It will stay at modified until something else flushes that out, just like what we did before. But the second I modify it, now I send a write bit that will be data snooped, right? And it will invalidate anything else. So now this is invalidated. And just like that, actually, I went through all 4 stages. Modified, exclusive, shared, invalid. Funny enough. So that's a good example of like how you can literally go through all 4 stages. So in the end, we had the modified value, we flushed it to get it exclusive, we shared the value to try to help out P1, P1 backstabbed us, changed the value, now we're invalid. All right, next part, P2, we're going to do a read to the register in 3. Let me just write this out, 8M, 8I. So this time we're going to be in P2, and this is going to involve cache address 3. What do we got here? We have 3I. Okay, well, that's not going to help us because, yes, this is the right address, but it's invalid, so we treat it as if it's empty. Let's see, can I get it from here? Because I would rather not go back to memory. Perfect, it's right there, it's modified. What do I got to do before I share it? I got to flush it. So just like before, this started out as 3M. I flush it to memory. Mem and cache are equal, exclusive. Now I can share easily. They're shared, they're happy, all is well in the world. This is a read, not a write, so there's no change in the value, no backstabbing takes place. Okay. Eight M, 3S, 8I, 3S. All right, P1. We're doing a read to the register. We're doing from mem address 1 to R1. So now P1 is going to be over here. Let's see, what is in that cache block to start off with? We have 1, 1, that's a modified version. And our other cache block has 5 and E. Okay, so that means that this P2 is not helping us, but we don't need it because guess what? Modified also means that we have the top version of it, the newest version of it. So for this one right here, we're just doing a simple read. I have to read it from cache because cache has the updated version. Main memory is going to have something outdated. It's going to have something stale. So I actually don't have to do anything in this case because this is a read hit. This M shows that it has the modified value. I take that value right from the cache. So whatever that value was, I could just take it like that. No problems, no changes. All right, 2 more, and then finally done with Mesi. We have a write to the mem address here in P2. So let's see, we got 8, 1, M, 3S, 8, 2, 3S, and we are doing a write, mem address 1, 1, what is there originally? A 5 and an E. And what do we want to do? We're doing a write to mem address 1. So first we need to allocate it. And to allocate it, we got to allocate it from here. Problem, we got an M here. Got to flush it before we share it. We always have to allocate first. We flush it, goes to memory, we share it. We share it. They both have address 1. Now in P2, I'm going to write. I'm going to change this to something else. Because it's right back, I stay in the modified state. I send an invalid bit because now this is invalid. Look at that. Messy yet again. And that is it for that one. Okay, last one, write to the address, R1 to 5. Well, that goes right here. I can't get it from anywhere else because it's not offered anywhere else. This is invalid. I can just treat it as empty. I could load it in from memory. It's going to end up taking a little longer. I'm in the wrong thing, aren't I? I'm supposed to be in P2. And because of that, there is a modified state here. And that modify needs to be flushed before we change the value. We flush the value, it goes to main memory. Now that it's exclusive, they're equal, I can feel free to just change the value. I overwrite this to be a 5, I take that from main memory, can't take it from the cache because it's not in the cache. And this is now exclusive, but this time for the 5 instead of the 1. And that's the end of that question. And the end of Mesi, if you want to take a picture.
For that into the last one, can you explain again why it's starting at E?
Yeah, of course. So his answer says shared, but technically it is starting at E because what was here before? It was a 5 and it was exclusive. Right? We got that from up here. It was 5 and exclusive. It was empty. It's not empty, sorry. It was not filled with the 1 that we wanted it to be. So we started at 5 and exclusive. We then shared it, but before we shared it, we had to flush the value. So we went from modified here to exclusive. Now I could share it. They both become shared with 1. Then I modify it. And that modification tells me to invalidate anything else. So the reason I have the exclusive here is because it was exclusive for what it was before.
Oh, so we're just overriding the address. We keep the state then?
Well, this was exclusive for the 5 and the 1 that were there. Sorry, the 5 that was initially there. It came from up here. There was a 5 that was exclusive there. No other change happened in this spot until that. So that spot, I know I had it empty here, but I just did not want to rewrite it every single time there. So because of that, this was originally a 5 and an E was here. So when we came to rewriting it, we shared the box over, right? And that changed it from exclusive to from 5 to the shared address of 1. I'm just taking the original value that was here. Like it's going from a 5 and an E here to being a 1 and an S. All he really cares about is the final state.
Alright, got it. Thank you.
No problem. Yeah, I mean, he has at the end, like, just S and M, because technically, when it was changed to a 1, it was an S. But before then, technically, before anything was changed there was an exclusive 5 there.
Oh yeah, on another note, for that one, it's still in modified. Can't we move it to exclusive since it's the only one that has that exclusive address?
Well, there's not, remember this is right back, so we're staying in modified until something flushes it out. Even if it's the end of the program. The only reason you're exclusive, the only reason you're exclusive is when cache and main memory are equal.
Okay, but in this case, it's because cache is updated but not main memory, so we just leave it as is.
Exactly. So if there was another instruction that was reading a value from that or something, and we had to share the value or something, that would automatically flush the value out, then we would change it. But there's no reason to. The only reason that you're flushing a value into main memory is to save it when you need to use the cache for something else. If it's the end of the program, you're not using the cache for anything else.
Okay, and this is only for write back, right?
You got it. Only write back. Write through, you write right through, the modified state.
Okay, sounds good. Okay, thank you.
No problem. All right, we're almost there. Sort of. Let's do a little disk scheduling quick. A little bit of raid. And then we can call it a night. Only 3 more to go. So I'm actually going to pause the recording here just because it is getting a little long, and I'll do another one.